Nothing in our solar system should be moving like this. Not this fast. Not on this path. For centuries, astronomers have tracked comets that belong here, objects bound to the sun, shaped by familiar gravity, following predictable orbits. But 3I Atlas breaks every one of those rules. This object didn't form in our solar system. Its speed alone proves that. It entered already moving too fast to be captured, following a sharply hyperbolic trajectory that marks it as unmistakably interstellar, a visitor from another star system. And when scientists rewound its path through the Milky Way using Gaia's ultra-precise stellar maps, something unexpected happened. They didn't find chaos. They found patterns. A small number of stellar systems appeared repeatedly as potential waypoints in 3I Atlas's long journey. Not definitive origins, but strong statistical suspects. Today, we're going to examine the 3 most discussed candidates astronomers have identified so far. Each one looks convincing at first glance. Each has solid scientific reasoning behind it. By the end of this video, you'll follow the trail back through the Milky Way to the 3 star systems most often whispered as possible homes of 3I Atlas. Each convincing, each deeply unsettling. Suspect number 1, G137-55/G137-54, the strongest dynamical candidate. The first and most serious suspect is an ultra-wide binary system known as G137-55 and G137-54, identified through gaiadata 3 astrometric data. This system stands out for one reason above all others: dynamics. When astronomers traced 3I Atlas's motion backward through time, accounting for the gravitational influence of nearby stars, this binary produced the most dynamically significant encounter among all known candidates. In simple terms, if any known system meaningfully altered 3I Atlas's trajectory in the past, this one did so more than the rest. Ultra-wide binaries are especially important in interstellar object research. Unlike tight binaries or single stars, these systems create unstable and competing gravitational environments. Objects orbiting far from either star can be tugged in opposing directions, gradually gaining energy until they're completely expelled. In simulations, ultra-wide binaries consistently outperform single-star systems. When it comes to ejecting debris, icy planetesimals, comet-like bodies, and other small objects into interstellar space. That's why G137-55/G137-54 rose to the top of the suspect list. Its reconstructed close approach aligns better than any other known system with the last few million years of 3I Atlas's modeled trajectory. The geometry works. The gravitational influence is real. On paper, it looks like the strongest case. Why it's still unlikely? The problem isn't proximity, it's speed. 3I Atlas appears to have passed this system at a relative velocity far higher than standard ejection mechanisms predict. While binary systems can eject objects efficiently, doing so at this speed, without an extreme, finely tuned interaction, is statistically unlikely. Even the researchers who flag this system as the strongest perturber are careful with their conclusions. This encounter is intriguing, but not conclusive. In short, G137-55/G137-54 looks like the best suspect, but not a convincing culprit. Suspect number 2, at Mike A/at Mike B. A young system with plenty to throw away. The second suspect takes us in a very different direction. At Mike A and at Mike B form a young, active M-dwarf binary system, cataloged as gaiadata 3. This system attracts attention not because of perfect trajectory alignment, but because of its environment. At Mike is rich in leftover debris. Observations indicate the presence of a cold dust belt, a clear sign that the system still contains large populations of small icy bodies. These are exactly the kinds of objects that get scattered during the chaotic early stages of planetary formation. Young stellar systems are violent places. Planetary orbits shift. Resonances break. Gravitational interactions between forming planets and debris disks can eject enormous amounts of material into interstellar space. If chaos could throw something into interstellar space, at Mike would be the place to do it. Its binary nature adds another layer of instability, increasing the efficiency of gravitational scattering. That's why this system appears in multiple encounter analyses as a plausible candidate. Why it's still unlikely here, the problem isn't physics. It's time. Mike is estimated to be only around 25 million years old, extremely young on galactic timescales. Meanwhile, the kinematics of 3I Atlas suggest it has been traveling through the Milky Way for hundreds of millions, possibly billions, of years. Its velocity distribution matches an older thin disk population, not something freshly ejected from a newborn system. In other words, Mike may be capable of ejecting interstellar objects. It just almost certainly wasn't around long enough to eject this one. Theoretical power, practical limits. The third suspect is quieter, less dramatic, but scientifically compelling. Identified as Gaia DR3, this object is classified as a G3V star, a main sequence star similar in type to our Sun. That similarity matters. Sun-like stars with giant planets are the most efficient known ejectors of interstellar objects. In our own solar system, Jupiter and Saturn have expelled trillions of icy bodies over billions of years. Many models suggest that the majority of interstellar comets roaming the galaxy were launched by systems just like ours. A G-type star hosting giant planets fits the ideal theoretical profile for producing an object like 3I Atlas. That's why researchers take this candidate seriously, even without a dramatic close encounter. Why it's still unlikely distance is the killer. When scientists calculate how close 3I Atlas came to this star in the past, the separation is far too large to allow meaningful interaction with the star's planetary system or any extended Oort cloud-like region. At distances of tenths of a parsec, gravitational influence drops sharply. The probability that a comet-sized body was launched during such an encounter is vanishingly small. This makes the G-type star an excellent conceptual suspect, but a weak practical one. What the puzzle really tells us, so what do all these suspects have in common? None of them work perfectly, and that's the point. When astronomers step back from individual stars and look at the statistics instead, a clearer picture emerges. 3I Atlas behaves like a typical Milky Way disk object. Multiple analyses favor a thin disk origin, its velocity and direction matching the calm, ordered motion of stars orbiting within the galaxy's main disk. Can we identify the exact star it came from? No, not with confidence. After traveling for immense spans of time, even tiny gravitational nudges from stars, molecular clouds, and the galaxy itself slowly blur its trajectory. By the time 3I Atlas reaches us, its origin has been forensically erased. Astronomers can identify past stellar encounters. They can rank suspects, but they cannot name a definitive birthplace. And that may be the most important lesson of all. 3I Atlas isn't a messenger from a one-star system. It's evidence of a galactic ecosystem, where planetary systems constantly exchange material across vast distances. This visitor didn't just cross interstellar space. It crossed deep time. And somewhere out there, countless others are already on their way. Tell us your theory in the comments. Also, don't forget to like, share, and subscribe so you don't miss the next chapter in our exploration of the universe. Thank you for watching. See you next time.